So we've been talking about applications of trigonometry to various other areas in mathematics. We talked about complex numbers, and we talked about using trigonometry to represent where points are on a plane in a different way, polar coordinates. What we're going to talk about the next couple lectures is vectors. The idea behind a vector is that a vector is a directed line segment from an initial point to a terminal point that has two attributes that determine it completely. Namely, the attributes are its magnitude, that's how long that line segment is, and the direction, where it points. What that means is the vector is decoupled from a particular directed line segment in the plane. We could draw it here, or we could draw another one. Might look like it's parallel to it, the same length pointing in the same direction, and that represents not a vector parallel, that represents the same vector. It is the position of the initial point doesn't affect what the vector is. It's merely its length and the direction that it points in. If you do a vector this way, then there is naturally a right triangle kind of lurking in the background, and the vector's length determines the length of the hypotenuse of the triangle, and the vector's angle with the polar axis, or with the positive x-axis, this angle here, represents an angle. So we could do right triangle trigonometry, and that's going to come in handy to analyze how vectors behave. Vectors provide a new set of objects to do arithmetic on. Arithmetic operations like addition and subtraction make perfectly good sense with vectors. The idea behind doing it is to line up the vectors so that their successive paths follow head to tail, so that this vector, if we're going to do v plus w, we take the tail, where v points, the tail of v, and start w there, and then take the direction from there, and the overall direction is what is assigned to the sum v plus w. Just like you have the algebraic inventory that you typically take in an algebra course when you're studying how numbers behave, anytime you introduce an operation on mathematical objects, vectors are fine, then you'd like to see if the properties of that operation match what you're used to having. I mean, it's called plus, so it looks like an addition. So let's see what kinds of properties work. Vector addition is commutative, and this is kind of an interesting thing to do. If you'd have the vectors v and w, and look at what that diagonal is, you could as well translate the vector w and do it first, and follow that by v. And whether you do v plus w or w plus v, you end up at the same place. And that is the content of this statement, that vector addition is commutative. Sometimes you see vector addition described as the parallelogram law, because whether you do v plus w, you get two sides of a parallelogram, w plus v, you get the other two sides. And either way, what you associate with the vector sum is the diagonal of the parallelogram. What else? Vector addition is associative, just like associativity of regular addition of numbers. It doesn't matter if you group it so that it is for a sum of three vectors. If you group it so that it's the last two combined with the first, or the first two combined with the last, the end position, the vector ends up being the same either way. So you've got associativity that works. There is a zero element that works, and what would the zero vector be? Well, let me draw a picture of it for you. It has length 0, so it starts at a point and doesn't go anywhere, so it is a vector that has a 0 length and an arbitrary direction, and that's the zero vector, which when added to any other vector doesn't affect it. And lastly, there is associated with a vector its additive inverse that would give 0 back out. What would the additive inverse of a vector be? Well, if you go in a certain direction, a certain distance from a point, and you go backwards, that same distance and exactly 180 degrees opposite direction, those two vectors, if you combine them by the parallelogram rule, you go forward and then back, and you back where you started. That's the 0 vector. So the negative v exists as a vector, and it satisfies the property of an additive inverse. Let's keep track of what it looks like geometrically. So there's a vector v. Let's look at what 2v looks like. 2v is the vector pointing in the same direction but twice as long. You can see this length, and here it is once, and here it is twice. Twice as long in the same direction. That is 2v. How about minus v? Minus v is the direction opposite, so instead of going up, it's going backwards, but the length is the same. If you add by putting the head of minus v on the tail of v, what happens is backwards and forwards, and you end up where you started. That's what the 0 vector does. Let's try to set some things up. You can graphically combine vectors to get an expression. There's v, there's w, there's a vector u. First of all, let's do v plus w. So we're going to focus on these. Let me plot them in a way that will make some sense. There's v plus w. Let me go back so that you can see that all I've done was to switch to move w down and back 2 units to get v plus w, and v plus w looks like this by the parallelogram law. Another example. From v and w, let's go from v to 2v. Doesn't matter where you start it, but you have to make it twice as long. So I see v went over 2 and up 3. So 2v goes over 2, 4, over 4, and up 1, 2, 3, 4, 5, 6. Okay? And if w does that, then minus w, we'll put it beside it so that it goes in the opposite direction. Instead of aiming this way, it aims this way, but the length is the same, and the direction is still, that line segment has the same slope. Often, you'll want to keep track of a more general linear combination. So 2v minus w. Remember when we did 2v and what that looked like? That's this part of the line segment. Minus w is this part of the line segment. If you line it up head to tail, 2v minus w is that by the parallelogram law. If you're going to keep track of a vector in terms of its pieces, the direction, and the length, then the symbol with double bars, like an absolute value with double bars, is the conventional thing for how big v is, how long that line segment is, and that's the magnitude of v. And a special case is if the magnitude is 1. If that happens, then it's called a unit vector. What do the unit vectors look like? Well, let's think about in the coordinate plane, putting in an origin and going out 1 unit in any possible direction. The unit vectors all lie on a circle of radius 1 about the origin. So unit vectors are all 1 unit away from the origin for an endpoint if the initial point is at the origin. And that's all you need to specify what the unit vector is. If you keep track of vectors in terms of sort of a base set, like the elements of vectors, a way to do it in 2 dimensions is to pick, by convention, a unit vector, a direction 1 along the positive x-axis, so 1 unit out that way, and j, 1 unit up along the positive y-axis. Then you can keep track of an arbitrary vector as the combination A times I plus B times J, and A and B are the multipliers of those unit vectors. They specify a distance out. So this should be a familiar looking picture to you when you're keeping track of I and J, to see A times I moving A units out in the positive X direction, B times J moving J units up in the Y direction. And the parallelogram law in this case works out like a rectangle law because you're going A units over and B units up, and then the hypotenuse is the linear combination AI plus BJ, and you can keep track of that. So think about this as an inventory. Now we've got lots of ways of specifying where a point is in the plane. The point in the plane could be specified as an ordered pair. That looks like that's Cartesian coordinates. It could be specified as a vector sum. It could be specified as a complex number. We did that. That looked like A plus BI. And notice that this I is not the vector I, but the complex unit, the square root of -1, is what that represents. And that's another way to represent. And then we've got all the polar forms for theta here, and this distance up along the hypotenuse of the triangle is the length r, or the length absolute value of the complex number z, or it's the magnitude of the vector v here. No different ideas, just different descriptions depending on the context of the problem. So let's look at one. A position vector is a vector that is centered at the origin. So you're going to write a position vector as, say, A times the vector I plus B times the vector J. Let's do the bold-faced J and the bold-faced I to remember that these are the vector quantities. And so we're going from -2 to 3 in the X direction, the horizontal direction. That is 3 minus a -2, that's 5 units. And we're going from 1 to 4 in the Y direction. We're going from 1 to 4 in the Y direction, that's the vertical direction. From 1 to 4 is 3 units. And that means that the position vector starting at 0, you could think about that as 5 times I plus 3 times J. And that would be the position vector for the vector indicated as from the point P1 to the point P2. Look at what those numbers are and where they come from the numbers as they're given. Looks like I'm ready to do it underneath what I've got here. And here's a picture of what's happened. We're going from -2,1 to 3,4, and that is 5 units over and 3 units up. From the origin, it's 5 units over and 3 units up. Doesn't matter where you start and where you stop. What matters is how far in either direction you go. And from the origin, you're keeping track with these unit vectors, 5i and 3j. Let's do some combinations now. If v is 2i plus 3j, or 3i plus 2j, and w is minus 4i plus j, let's keep track of this linear combination, 2v plus 3w. So for A, we could do 2 times v, that's 3i plus 2j, plus 3w, and w is minus 4i plus j. And now you could do it algebraically by collecting like terms. 2 times 3i is 6i. 3 times minus 4i is minus 12i. 6i minus 12i is minus 6i. 2 times 2j is 4j. 3 times j, 3j. So 4j plus 3j is 7j. So that would be the linear combination for A. And for B, we want to calculate the length of V. And the length of V comes from the Pythagorean theorem formula, the square root of 3 squared plus 2 squared. 3 is a component, 2 is a component. So that's the square root of 9 plus 4, square root of 13. And that's the best I can do. That's how I should write it. If all we care about is the direction, then we can keep track of a unit vector that specifies that. Think about it this way. For the unit vector, since a vector in general consists of 2 attributes, a magnitude and a direction, if you throw away the magnitude, all that's left is the direction. So throwing away the magnitude is dividing by the magnitude, and we can find a unit vector by taking a vector and dividing by its length. So let's try one. A unit vector in the same direction as V equals 3i minus 5j. So that would be the unit vector is V divided by the length of V, which is 3i minus 5j over the length of 3i minus 5j, which is 3i minus 5j over the square root of 3 squared plus minus 5 squared, which is 5 squared. Well, let's see. 3 squared is 9. 5 squared is 25. 9 plus 25 is 34. So the square root of 34 is what's on the bottom. And it's 3 over root 34 times I minus 5 over root 34 times J. Those aren't particularly nice numbers, but that's how it comes out. I should have written these as that bold-faced I and J to have the vector quantity here. As I'm working my way down through here, these are vectors, the unit vectors in the I and the J direction. So 3i minus 5j. Let's look at what that does graphically. You could think about 3i as 1, 2, 3 steps in the I unit vector direction, minus 5j as 5 steps in the negative j direction, and then the vector 3i minus 5j is 3i over and 5j down, so it's that vector. That's way too long to be a unit vector. How long is that? Well, it turns out to be the length of V is that square root of 34 term that came out. So if you divide by that, you end up with a vector that is of length 1. And this is the vector of length 1 pointing in the same direction. And that little piece here, this little piece, is what we got as the unit vector in that direction.